Hi guys, this is Dr. J here, and in this particular video we are going to learn how to draw resonance structures. So basically, when drawing resonance structures, you should already know that we are trying to delocalize our pi and non-bonding electrons, right? So basically, when delocalizing these pi and non-bonding electrons, we are going to use curved arrows. Okay, so these curved arrows are going to indicate the movement of electrons. Okay, so they are never going to indicate the movement of atoms. So whenever we are drawing curved arrows in resonance structures, that means we are showing how the electrons move. And always these arrows starts from electron rich areas, and then it will always end from electron deficient areas. Okay, so basically these arrows will always start from something like a negative charge or lone pair and even a pi bond. Okay, but it will always go in the direction of electron deficiency. Okay, so it will try to go towards electron deficient areas like positive charges or things like that. All right, so let's try these resonance structure drawings using a few different examples. Okay, something that you might want to remember is that negative charges and lone pairs act similarly. Okay, and therefore whenever I discuss negative charges, it could be applied to lone pairs as well. Okay, so the first example that we are going to talk about is when you have a negative charge next to a pi bond. Okay, so in here I have a negative charge next to a pi bond, or actually two pi bonds. So let's see how to draw resonance structures for this particular compound. So I'm going to redraw this molecule. Okay, I'm going to redraw this molecule, but this time I'm going to color my pi bonds and the negative charges in different colors so that you can identify the difference. Okay, so here my negative charge is going to be orange in color, and my pi bonds are also going to be magenta and green. So you can see how these electrons are going to change. Okay, so we will start the movement of electrons from the richest area. So the most richest area of electrons is going to be the negative charge. Okay, so we will start from there. Okay, and you can go either direction. Okay, so let's go clockwise in here because both clockwise and counterclockwise look similar, so you can go in either direction. Okay, so we are going to uh, take these two electrons on the negative charge and we are going to put it in between these two carbons. If you do that, this carbon right here, okay, it is going to have too many bonds. Okay, it already has three carbon bonds and a hydrogen, right? So it is going to have too many bonds. Remember, there is a hydrogen here. Okay, so it is going to have more than four bonds. That is not allowed. If that is the case, you should break a bond. So the bond that you will break is not a single sigma bond. The only bond that you can break is the pi bond. Remember, in resonance structures we are moving pi and non-bonding electrons, never touch any sigma bonds. Okay, so let's see what we got. Okay, here is our resonance arrow, and then we have an orange pi bond now, and then we have a magenta negative charge, and then orange bond was unchanged. Okay, nothing happened to the nothing happens to the green bond. Okay, so are we clear? All right, so let's move it around. I mean, we can go further actually. So now we can move this negative charge between these two carbons and then break the green bond onto the top carbon. Okay, so if you do that, you will get something like this. So you are getting a magenta bond between these two carbons and then a green negative charge, and of course then the orange pi bond was unchanged. Okay, maybe we can move further. Okay, we can move further. Let's do that. So let's try to let me use a different color. Let's try to bring this negative charge onto these two carbons as a pi bond. So if that is the case, this carbon is getting overloaded. Okay, so you want to move that pi bond onto this carbon right here. Okay, so this carbon gets a bond, so this carbon should get the 2 electrons on the pi bond. If that happens, you will end up with something like this. Here's your pentagon, and then magenta bond is unchanged, we didn't touch that, and then your green electrons will make a pi bond, and the orange electrons will be a negative charge. Okay, so these are the 4 resonance structures that I have drawn. Okay, they are all different from one another. Of course, they are all different from one another. You can see if you can draw more. Okay, and here's the thing, you should try to draw something different, something that is not already included here. Okay, all right, so all these are resonance structures. Don't forget to put the resonance bracket, and those are resonance structures of the structure that we had before. All right, so that is how you do or that is how you write resonance structures if you have a negative charge next to a pi bond. So here's another example. I want you to pause the video and see if you could do this one. In here, once again, you have a negative charge next to a pi bond. See if you could draw resonance structures. All right, so you will move the 2 electrons on the negative charge towards the pi bond. So you're trying to make a pi bond between these 2 carbons. And also, if you do that, this carbon already has 4 bonds, so it will have 5 bonds. So we need to break a bond from this carbon. So you will break the pi bond and take it onto oxygen. If you do that, you're going to get a pi bond between the 2 carbons, and then a negative charge on oxygen. So these are the only 2 resonance structures that you could draw. Okay, so here is the resonance bracket. All right, guys, so now if you have a negative charge or a lone pair next to a double bond, it is easy. Okay, it is easy. So I would recommend that you guys practice a little bit more with more examples. Okay, so I will give you a handout so that you can try different resonance structures like this, but never break any sigma bonds. Okay, never break any sigma bonds. And if I ask you this question, out of these 2 resonance structures, which one is more stable? Which one is more stable? Let's call them A and B. Which resonance structure is more stable? Of course, B will be more stable. Why? Because on B, the negative charge is on oxygen. Okay, so on A, the negative charge is on carbon. So if you consider electronegativities, electronegativity of oxygen is way higher than electronegativity of carbon. So therefore, if you have a negative charge, it prefers to stay on top of the more electronegative atom, which is oxygen. So your negative charge is on the more electronegative atom, which is the more greedier atom, right? So this B, the resonance structure B, is actually more stable as compared to resonance structure A. All right, let's try another example. Okay, in here I have a negative charge next to a positive charge. Okay, I have a negative charge next to a positive charge. Let's see how to do this. So I'm going to do a small change to this structure. I'm going to color code my non-bonding and pi electrons. So I'm going to use, let's say, blue color for my pi. All right, so I just color coded my pi bonds and non-bonding electrons so that you can visualize the electron movement better. All right, so you always start with the more electron rich area, which is the negative charge, and you will bring this negative charge between nitrogen and oxygen. Okay, so you are making a pi bond. If you do that, this nitrogen is going to have 5 bonds. Why? Because it already has 1, 2, 3, 4 bonds. So nitrogen can only have 4 maximum bonds. Okay, so if you are making a new bond, you should break something. The only thing that you should break is the pi bond, and it will go on to oxygen. Okay, if that happens, you will have a molecule like this, CH3. Nothing happens to CH3. Nitrogen will have a single bond with previously double bonded oxygen, and the pi bond will be a negative charge on oxygen now. Then you also have a double bond with the bottom oxygen. All right, and check around nitrogen. You have 4 bonds, and of course the positive charge will also be there. Okay, positive charge should also be on nitrogen. I mean, you can try to calculate formal charges, but here's the thing: when you are doing resonance structures, overall charge should always be the same. Okay, so you started with an overall 0 charge. Why? Positive charge cancel out the negative charge, so this molecule right here has a 0 charge, or it's a neutral molecule, overall neutral, right? So once you draw the other resonance structure, it should also be overall neutral in charge. So nitrogen should have a positive charge. Okay, and of course in the beginning your nitrogen had 4 bonds, at the end your nitrogen has 4 bonds, so nothing changed. Okay, nothing changed. So even though we are moving pi electrons, nothing actually changed when it comes to bonding, right? All right, so let's do another example. Okay, here is an example that I want you to try without my help. Okay, so see if you could pause the video and try this. Okay, so in here, once again, you have a negative charge next to a positive charge. So what you do is you will always start your arrow, the movement of electrons, from the more electron rich area, which is the negative charge, and you will break it, or you will make a new bond between nitrogen and oxygen. Nitrogen already has 4 bonds, triple bonds, and a single bond. So if you are making a new bond, nitrogen is getting 8 bonds. 8 bonds is 10 electrons. Nitrogen can only have 8 electrons. So you have to break a bond. So break this one of the pi bonds from this triple bond onto carbon. Okay, if you do that, you will get something like this. CH3 is unchanged. Now this carbon has a negative charge from that pi bond, and then you only have a double bond between carbon and nitrogen. Okay, and then you made a new bond between nitrogen and oxygen, so it should have 2 bonds between nitrogen and oxygen, and here's the positive charge. You started with 4 bonds around nitrogen, you ended with 4 bonds around nitrogen, so positive charge must be there, and overall the molecule is neutral. And here is your resonance bracket. Don't forget to do the resonance bracket. Okay, do not forget to do the resonance bracket, resonance arrow and resonance bracket. Keep that in mind. Okay, all right, so in the third scenario, I'm going to draw resonance structures when you have a positive charge next to a pi bond. Okay, let's talk about a scenario where you have a positive charge next to a pi bond. Okay, so here's the example that we are going to try. Okay, I'm going to use a different color, of course, so that you can visualize the differences. Okay, so you will start with the pi bond. Of course, your arrow will always start with the more electron rich species, which is the pi bond. And now you will make a new bond between this carbon and this carbon, right? If that is the case, you are no longer going to have a double bond between these 2 carbons, but you are going to have a double bond between these 2 carbons, and the positive charge will actually migrate all the way to this side. Okay, all the way to this side. All right, as you can see, this carbon right here, let's call it number 1 carbon. 1 2 3, 1 2 3. So number 1 carbon had 4 bonds before. How do you know it had 4 bonds? Because, I mean, of course, this is a skeletal structure. It only has 2 carbon-carbon bonds on this carbon, so it has to have 2 hydrogens. It has to have 2 hydrogens. So when you are moving a carbon-carbon bond onto the other side, this carbon lost a bond, right? This carbon lost a bond, so it only has 3 bonds, so that is why it is positive. That is why it is positive. Okay, that is why it is positive. So always count the bonds, okay, and then give the appropriate charge. Of course, this carbon, it's a positive charge, which means it had 2 hydrogens. Okay, but it only has 3 bonds. That is why is it positive. It is positive, and then now it has 2 hydrogens still, and this carbon has 4 bonds, so no need to have a positive charge. So you are basically migrating the positive charge. You are migrating the positive charge to a neighbor carbon. Okay, to a neighbor carbon. Actually, you are moving it 2 carbons away. Okay, you are moving it 2 carbons away. All right, so I want you to pause the video now and then see if you could draw resonance structures to this particular molecule. All right, so let's start with this pi bond. Why did I start with this pi bond? Because it is, of course, next to a positive charge. So this will be the more rich area. So your arrow should start with the pi bond and make a new pi bond between these 2 carbons. Okay. So nothing happens to the other carbons. So you are getting a new double bond here, and the positive charge will be right here. Then you can further delocalize this positive charge. You can use the next double bond and then draw another resonance structure, of course. And then in here what happens is that this carbon will get the positive charge, and then the double bond will shift by 1 carbon. Okay, so in each of these situations the double bond will shift by 1 carbon and the positive charge will shift by 2 carbons. Okay, the positive charge will shift by 2 carbons. It was on, let's say, carbon number 1 before. Now it is on carbon number 3. After that it is on carbon number 5. See, it is always shifting by 2. Double bond shift by 1 carbon, positive charge shift by 2 carbons. All right, so these are the only 3 scenarios that you will always use. Okay, so whenever negative charge is next to a pi bond, when a negative charge is next to a positive charge, or a positive charge next to a pi bond. Okay, but here's the thing, you can't learn this resonance structure by just watching this video. You have to always try more examples. Okay, so practice will make you perfect. Okay, but I mean, until you draw at least like 10-20 resonance structures, your brain will not, or your brain might have a hard time understanding resonance structures. So I would recommend you to try this molecule. Okay, try to draw some resonance structures for this particular molecule. All right, and then I will show you how to do it. Okay, I will show you how to do it. And there's a small mistake. There is a positive charge right here. All right, see if you could draw resonance structures to this molecule. So it's a positive charge next to a double bond, right? So move it around. Actually there is a small mistake in this molecule, so let me rewrite it. Okay, let me rewrite it. So let's say positive charge is right here, and these are the 2 double bonds. Okay, so now you can see if you could draw resonance structures for this structure. All right, so it's a positive charge next to a pi bond, so you will use the pi bond, move it 1 carbon, and then positive charge will migrate 2 carbons. Okay, and then you will have something like this. You can further migrate it, of course. If you do that, you're going to get a resonance structure like this. Your new double bond is here. Positive charge will migrate to this carbon, hydrogen, electrophile, double bond, and in NH2. Those are unchanged. And that's pretty much it. I mean, that's all you could do. Okay, so these are the 3 resonance structures for the molecule or the ion that I showed you before. All right, and let me do a small change. And then see if you could draw more resonance structures to this particular compound. We're going to do the same aniline. It is very similar to the previous structure, but only difference is now your positive charge is actually a little bit to the, I mean, it has moved by 1 carbon. Okay, so let's see if you could do this one. In here the electrophile or E group is in para position, Okay, in here in the previous one it is on meta position. Those are things that you will learn later on. Okay, but let's see if you could draw resonance structures to this molecule. All right, so we will start with the pi bond next to the positive charge, and then you will move it, so you're getting a new double bond over there. Electrophile is unchanged, or E group is unchanged. All right, this is one. And then what you could do is you can use this lone pair and then make a new double bond between nitrogen and positive charge. Okay, so whenever you have a positive charge next to a lone pair, you can do this, and then you will get a resonance structure like this one. So positive charge will migrate onto the nitrogen, and then the rest will remain the same. Okay, and you could also draw another resonance structure. Okay, let's say if you use this double bond, you will get something like this. All right, so these are the 4 resonance structures that are possible. Okay, so what I did was, rather than using the lone pair to get this resonance structure, I moved the double bond towards the positive charge and then shifted the positive charge 2 carbons down. Okay, so all these 4 are possibilities for resonance structures. Okay, see if you could get them by yourself. Okay, see if you could get them by yourself. And of course, if you need more examples, I would recommend you to try your hand out and let me know if you have any questions. Okay, guys? All right, with that, I'm going to conclude this video. Please let me know if you have any questions. Take care.